Hello everyone, I'm Justin Morris, and today I'll be giving a talk about AdaptBit HD, a technique for adaptively changing the bit width of a hyperdimensional computing model. First, I'll talk about the basics of hyperdimensional computing, or HDC. HDC works by first taking all of the samples belonging to a single class and encoding them to high dimensional space, where D is 10,000, and we'll call these hypervectors. Then we combine all of those samples belonging to a class together to create one hypervector representing the class. Then we do the same for the rest of the classes. Now we have a model with which we can use for inference. To perform inference, we first encode the sample image into a hypervector using the same encoding used during training. Then perform a similarity check to check the most similar class hypervector. This similarity check can change based on the data representation. For instance, floating point values might utilize cosine similarity, while binary ones may use Hamming distance. One problem with HDC is encoding the original feature vector into high dimensional space. This leads to issues with data storage, energy consumption, and execution time. And prior work alleviated this issue by quantizing the hypervectors. For instance, Brick introduced a new binary encoding and also created a binary HDC model. QuantHD built upon this by introducing a ternary quantization to reduce the accuracy loss of going to lower precisions. However, one thing that all prior work lacked was the ability to adaptively change the bit width at a granular level. Instead, all prior work quantizes all samples to the same bit width. In this work, we introduced a new method of quantization for HDC, where we can adaptively change the effective bit width per sample to achieve a balance between energy efficiency, execution time, and accuracy. This graph compares the accuracy of different HDC quantization levels. We can see that 16-bit or full precision is able to achieve the highest accuracy, but would be the least efficient. We can also see that there is a cost in accuracy for going to binary. However, binary would be the best efficiency. And we can also see that statically quantizing to 5 bits gives a decent balance between accuracy, energy efficiency, and execution time. However, we can see that most samples are easily classified with binary representations. So there's a lot of wasted effort if we quantize all samples to 5 bits. It would be better if we could adaptively change the bit width for each sample to save energy and time when the sample is easily classified. That is what AdaptBit HD aims to do. Before going over how AdaptBit HD works, I'll first go into more details about baseline HDC. During the similarity check, we have two high-dimensional vectors where we need to calculate a metric for how similar they are. Typically, for any bit width beyond binary, we would use cosine similarity as that metric. In this case, we have a bit width of 5, so to calculate the similarity, the fastest way possible would be to perform a costly 10,000 multiplications, accumulate the results, and divide by the Euclidean lengths of the vectors. Binary quantizations improve upon this by simply counting the number of mismatches with XOR gates and accumulating the count. However, there is an accuracy loss for going to binary. In AdaptBit HD, we use a 5-bit quantization model, but fundamentally change how we operate. Rather than calculating a costly 5-bit multiply across all dimensions, we utilize Hamming distance just like the binary model and operate 1 bit at a time. For instance, here, we will get the Hamming distance for the first bit, and the first bit is the sign bit, so this operation is functionally the same as the binary quantization. Then we check if the similarity is past the threshold we find during training. If the threshold is not passed, we move on to the next bit and continue accumulating the Hamming distance calculation. We then check the threshold again, and this time it passes, so we terminate execution. If the threshold is never met, we simply take the output after passing over all of the bits. Here we compare the accuracy of AdaptBit HD with static quantization methods. We can see that AdaptBit HD is 1.1% more accurate than binary models for HTC, and AdaptBit HD is comparable in accuracy to full precision. Furthermore, AdaptBit HD is 16x more energy efficient and 15x faster than full precision. This means that AdaptBit HD is able to achieve the accuracy of full precision with comparable energy and execution time to binary. This is good for applications where there needs to be a balance of accuracy, energy, and execution time. For example, a medical device running on a battery diagnosing a patient. And these results were obtained using a Kintex 7 FPGA using Verilog HDL as our design language. And here we compare the energy consumption and execution time of AdaptBit HD with other static models. The results are normalized to full precision, which is 16 bits in our case. And the different bits show the energy consumption breakdown that AdaptBit HD uses for each bit. We can see that over 90% of energy is used on the first bit because AdaptBit HD terminates execution at the first bit, like binary, 90% of the time. Finally, we can see that AdaptBit HD only incurs 10% more energy and 7% more execution time than binary. So, in conclusion, prior HTC work alleviated the problem of space, energy consumption, and execution time of HDC encoding to 10,000 dimensions with static quantization. With AdaptBit HD, we introduced the first adaptive Bitwidth quantization for HDC. AdaptBit HD maintains the same accuracy as full precision models, which is 1.1% more accurate than binary, and achieves 14x energy efficiency and 15x execution time improvement over full precision models, which is comparable to the improvements we see with binary. And this is good for applications that need to balance accuracy, energy, and time. So AdaptBit HD enables high accuracy, energy efficiency, and execution time all at the same time. Thank you.